Okay, can you see the screen?
Yes, we are already live on on YouTube.
Okay, okay, so let's get started. Today I'm going to talk about testing and estimating treatment effect in the presence of a delayed onset of the effect of cancer immunotherapies. This is a joint work with my colleagues Changyu, Hui Nian, and Philip He. Um, okay, so the outline, the first we want to uh, talk about the motivations and of our proposed methods, and then we will present a weighted log rank test to accommodate the testing delayed treatment effect, and then we will conduct a comprehensive simulation study to compare actually our proposed method with the existing uh, standard log-rank test and other weighted log-rank tests. And also we want to talk about a little bit about the estimation, how to estimate the delayed treatment effect. And then we'll have some discussion. The motivation is like in the cancer community, they now the hot topic is like how to design effective immunotherapy. The difference between the immunotherapy and other traditional therapy is that there would be a delayed treatment effect in the immunotherapies. It's not like the chemotherapy or other therapy. Um, the immune system need time to build up its immune reaction or immune response to the treatment. So when we design a trial, how can we accommodate to this delayed treatment effect? And this is a real data set from lumbar, kind of head and neck cancer. This is the overall survival chart, and so clearly you can see there's two groups, control group and a control arm or experimental arm. Um, so from the graph, you can see clearly, like when we start the trial, then like before 3 months or 4 to 4 months, there's no separation between those two survival curves. So basically, that means the treatment effect uh, has not been shown until like late, like after months of treatment. And then after like 5 months, the separation is clearly presented, and it would be wider and wider separated. So, how to accommodate this effect and the delayed treatment effect? We know the standard log rank test is used widely, but that is under the assumption that the survival curve would separate at the very beginning. Like when you apply the treatment, there will be effect shown at the very beginning. Otherwise, so under that proportional hazard assumption, the standard log rank test is considered the most powerful test, the method to use. But if there's a delayed treatment effect, then the standard log rank test will not be the most powerful test anymore. So that's why people design some all kinds of weighted, so-called weighted log rank test. And also our method is also try to take account of the delayed treatment effect. And so that's our motivation. So basically, the setup and the notation, we use the Schoenfeld notation in our throughout our research. So the setting is like that. Suppose we randomize any subjects in two treatment groups, control and experimental. And also, we suppose D is the set of subjects who experience the event. And there's a time J is the event time. And also NIT is the number of subjects at risk right before time T for those two treatment group. And PT is the portion of the number of subjects at risk in treatment group over the total number of subjects at risk. And so the Schoenfeld in 1981, he proposed that this test statistic is using the notation I just presented. Here, the WJ is a weight term, is a weight function. And when we take the WJ is 1, so that would be the standard log rank test. So there's no and if we choose different kind of weight function, will give us different weighted log rank tests. Why did I use the weight function is so-called Fleming-Harrington test, which is the weight function is taken as a function of the pooled estimate of the survival function at time t. And it's actually not a one test, it's a group of tests because it depends on the parameters, rho and gamma. So when rho is 0, gamma is 0, this is just 1. This is the standard log rank test. And if we let rho is 0 and the gamma is a number bigger than 1, so that would be a kind of weighted log rank test, put more weights to the late events. And if we set the gamma is 0 and the rho is bigger than 0, that would be another kind of weighted log rank test, put more weights on the earlier events. So here because we are talking about the delayed treatment effect. So generally we will think the Fleming-Harrington test would be proper to use if we set a rho is 0 and gamma is some positive numbers. But then the more appealing intuitive way is so you see this weight function is a function of the survival function. But if we want to we are interested in the delayed time, so why not we just directly set a weight function as a function of the survival time, not just the survival function. So that's our motivation. Okay, so we consider a hazard ratio model in this piecewise function. There's a 3 pieces. So first, there's a no. So the hazard ratio is 1. That means there's no treatment effect take on. And between time tau 1 to tau t, we call this is a transition time period, so that the hazard ratio is changing smoothly changing from 1 to lambda. Eventually, after time tau 2, the treatment effect will take a fully will take effect fully. So basically, this is a an approximation, but it's a plausible model to model the delayed treatment effect.
Lambda greater than 1, right?
Lambda is lambda is less than 1.
Less than 1. Okay, thank you.
Yeah. So this is a non-decreasing function of time t, and actually there's a simplified model. So suppose there's just a time tau star. So there's it's not so for hazard ratio, it's changing from 1 to lambda, but it's not smoothly changed. It's like there's a jump at time tau star. So a simplified model is like there's just two pieces of the function. What the lambda t is first is 1 at a certain time, and after tau star it will be lambda directly. So then there will be like a step function. But our model is like a little bit complicated to that simplified model. So we suppose there's a transition period, so that the hazard ratio will changing smoothly from 1 to lambda.
Okay, so Xiang, so lambda is I guess is between 0 and 1. Yes.
Yes. Lambda is a positive number. Yeah.
Positive number. Yeah, positive number and
less than 1. Yeah. Less than 1, that means the treatment, there's a treatment effect. Yeah.
So you mean this function is smoothing? It's a
linear function.
Is it
it's a continuous. Sorry, it's a continuous function. It's not smooth. You can see when t is
at the tau 1. At the tau 1
is tau 1 it is 1, and at tau 2 it is lambda.
Lambda, yes.
Yeah, but it's not smooth. Sorry, it's
continuous.
Continuous, yes, continuous, yes. Yeah, in the middle we just suppose this is a linear function of t. Okay, so that's not the perfect, that's not a true model, but actually it's an approximation, so that because the cancer immunotherapy research community believe for immunotherapy to take effect, it needs time to build up, and so it's not like the treatment effect will jump directly from 1 to a certain number. It may build up gradually. So that's why we consider these models, so that the hazard ratio will changing continuously from 1 to lambda. So then if we based on this model, so we can design our weight. So we propose a weight is very intuitively. So suppose we have a weight function like in this form. This is like a sigmoid function. So when t is this function is changing from 0 to 1 smoothly, smoothly, and when t is tau and a is two parameters. When t is tau, it's 1/2. It's at the middle of between 0 and 1, and this parameter, another parameter alpha, will control the width of the control the width of the transition period. And furthermore, we can consider modified weight. So instead of changing from 0 to 1, we can chomp the head and the tail a little bit, so that we can make it more specifically. The transition period is from tau 1 to tau 2, and then before that it's just the 0. The weight is 0. That means we don't think anything about the treatment before tau 1, and after tau 2 it's just 1. The weight is 1. So we fully take into account of the treatment effect. This is just a slightly modification to our previous weight function. So we can see the graph of these two weight functions. the green one is actually the smooth one, the sigmoid function. So you can see there's a very small weight before time t1. So and after t2 there's like a 9.9 weight of the t2 and going to 1. And the width of the t1 to t2 can be controlled by the parameter a. And the modification of this weight is the red dot light. So that means before t1 we just think the weight is 0, and after t2 the weight is just 1. But between them we can use a sigma function to connect them. So we will check we will apply these two weight functions to the our proposed weighted log-run test. The theoretical result is like this. Schoenfeld proved that this test statistical in Formula 1. This test statistic actually has asymptotically normally distributed with mean mu and the unit variance. The mu, so Schoenfeld give an approximation of mu in this form in Formula 6. Basically, you can see mu is n is the sample size, n 1/2 times a ratio between two integrals. It's a very complicated integrals. In some simplified model, it could be calculated analytically, but if the model is very complicated, there's a challenge to how to calculate these integrals.
What is VT in the formula?
In the VT and the pi-t, it's just some also further complicated expressions. Okay. So basically, our method is based on these results. So now the question is how to. So we know the approximation of mu and how to accurately evaluate the mu, because we know that the sample size and the power, sample size calculation and the power evaluation depends on the calculation of the mu. Here, R is actually just the term I mentioned. R is mu over n to the 1/2, which is just this term, this whole bunch of things. This is R. This is our challenge here. So if we know R and we know the power, we can calculate the sample size, use this formula. And also, if we know the sample size and we can calculate the mu basically means R, then we can also evaluate the power. So basically, we are trying to use numerical method to calculate the Schoenfeld approximation. So how to use, so we just apply numerical method to calculate this term. And then further, we can get approximation of the Schoenfeld approximation. So we conducted comprehensive simulation to compare our proposed weighted log-run test with standard log-run test and three weighted log-run tests using Fleming-Harrington weights. The simulation algorithm is like this. Suppose we have n subjects. We put it in two arms, control and the treatment arm. And so for the control arm, that's just, we follow an exponential distribution. So there's a H norm. The hazard of the control arm is H norm. And for the experimental arm, so there are several ways to design the experimental arm. We can assume that the same exponential distribution as control arm. That means there's no treatment anyway. So basically, they are just saying we use this to evaluate the type 1 error rate of the various tests. Or we can just suppose the experimental arm has a lambda times h norm distribution, exponential distribution. So that means there's no delayed treatment effect. So at the very beginning, they should be separated. And so that is called no delayed treatment effect. And then further, we can design different lambda t times h norm for the experimental arm. Then in that case, there will have a delayed treatment effect, and how those tests will perform. So we try to compare their performance. And this is how we determine the observed survival time and in the simulation. And then we will apply our proposed weighted log-rank test using weighted 3 or 5, and also the standard log-rank test and three tests in Fleming-Harrington weights. So first, we just suppose that the control arm and the experimental arm is just same. So we try to evaluate the type 1 error rate for our test, and for comparison using the standard log-rank test. Basically, theoretically they should be close to 0.05 because we suppose the alpha is 0.05. The nominal alpha is 0.05. So that will assure us at least that our test and the standard log-rank test just behave normally. And then another scenario is that there's no delayed treatment effect. So the control arm and the experimental arm, the hazard ratio is always a lambda. In that case, we use the sample size is calculated using our numerical evaluation of Schoenfeld approximation. So we suppose there's the power is 85%, and we use our formula to calculate the required sample size. So we tried 3 scenarios sample size. It depends on the different hazard ratio, 0.5, 0.6, or 0.7. We calculated the 3 different sample size, and using that sample size, we run our simulation, and using the test to check if that. So in this scenario, the log-rank test is supposed to be the most powerful test. So that is true actually, because we suppose it is 85% power, and the log-rank test is give us close to 85% power. But our proposed weighted log-rank test has the power is less than 85%. So you can see we tried 3 different transition period. One is between 30 days to 60 days. The other is 60 to 120. And all are lower than 85. That is as expected, because in this scenario, log-rank test, standard log-rank test is the most powerful one. Then and this one is for the transition period 90 to 180. days. Here we have the scenario is like suppose we know the true case is the transition period is 90 to 180. So we run a simulation and the control arm has the H non exponential distribution, and the experimental arm would have the delayed treatment effect, and the transition period is 90 to 180 days. So in that scenario, we applied those 6 tests to the simulation data, and we check the power, the empirical power for all those tests. Our method is these two, is the green one and the light red one. So these two are behave very closely. You can see it's close to 85. Suppose the power is 85%. And this one is the Fleming-Harrington weight with rho is 0 and the gamma is 0.5. And the light blue one is the Fleming-Harrington weight with rho is 0, gamma is 1. Another one, the purple one is rho is 0, gamma is 2. And the standard log test is this dark blue one, is close to 75% in the middle. So in this scenario, our methods is behaved as expected, is close to 85%. That is because we know the true case. The transition period is 90 to 180. So the simulation data is generated in this way, and then we use the correct method. So this is as expected. It should behave powerful than other tests. And also, we try different transition period. These 3 transition periods using the same simulation data generated. So if we know the truth and we apply the correspondingly, we use the correct weighted log test as we proposed, then the power behaves better than other tests, because other tests may not accommodate to the correct hazard ratio model.
So as some ratio value is even bigger than 85%. Yeah.
Oh, yeah. Some is bigger than, but some is less than, but on average, it's close to that line. And also we tested on 3 survival rates, because the survival rates basically tells us the lambda, the number of the value of lambda, because survival rates means after follow-up time, how many will survive, like 40% or 50% or 60%. That totally depends on the hazard ratio lambda. And in these scenarios also, if we know I think the transition period didn't mention, it's actually from 90 to 180 days. And we see the similar performance here. Our method is close to the 85%, because the simulation data is generated in that way. So what if because in real world, we actually don't know the what is the transition period, what is the true transition period for the clinical data. So okay, so this one is the table of our graph actually. This table tells us if our method to calculate the sample size is accurate or not. Here, there's two ways to calculate. One is if because we propose two ways. One is 3, one is formula 3, one is formula 5. They are actually pretty close. So suppose we just design the trial based on the weight function 5, which means the weight is from 0 to 1. There's a truncated period from 0 to 1. So based on that, we can, if we want to have 85% power, how many sample size we should need. So we can calculate the corresponding sample size. Depends on different hazard ratio. Then after we generated using this sample size to generate the simulation data, we can apply all those 3 log-rank tests to the simulation data to check what is the empirical power. What is the empirical? So we know it should be like 85%. Then you will see that from the table, you will see that our two proposed weight will give us the empirical power close to 85%. But the standard log-rank test, because it's not the correct test to use, so you will see there's a power loss when we apply the log-rank test. So in that way, that means the calculation of the sample size makes sense because the empirical power confirms that it actually gives us the designed power. But if we use different, if we calculate the sample size based not on our proposed weight, but just based on the log-rank test, that means the weight is 1. In that case, we can calculate different sample size. We can compare these two. So because this is there's a true transition period there in our simulation data, but we calculate the sample size based on the log-rank test. So you will see there's a inflation of the sample size. So we need more sample to accommodate the different the log-rank test. But anyway, we calculated the sample size and we generated that many sample using the simulation algorithm. And again, we tested the empirical power using these 3 tests. And in this case, the log-rank test gave us the empirical power close to 85% as expected. And the other two will give us more power because they are actually giving because the sample size is more than they needed, so it will give us more power here. Again, that shows the calculation of the sample size and even the power evaluation that does works here. So the last simulation study is like this. If we can generate the simulation data, so we know the true transition period. But if we apply the wrong weighted log run test, because if we're using the wrong transition period in the weighted log run test, how would that perform? So we know the true transition period is from 90 days to 180 days. Okay, so that means for this transition period, the midpoint, the center is 135, and the width is 90 days. Okay, so for the transition period, we can either use two endpoint to denote this transition period, or we can use the center with width to denote the transition period. They are equivalent. They are equivalently same. In this scenario, if we know the true transition period is 90 from 180, we can calculate the sample size, the needed sample size, if we're using the correct weighted log run test. And then we can we generated that many samples, 232, and as our simulation data set. And then we can apply these 5 tests to check the empirical power. Okay. So in this case, if for the transition period, when we're using these weighted log run tests, the transition period is corresponding to the true one. So that will give us the expected empirical power, 85%. And the other 3 weighted log run tests for Fleming-Harrington weight will give there's a power loss there. Now, also for standard log run test, there's also a power loss. It's around 75%. And if we apply, so using the same, yeah. So now, what if the true transition period is here from 0 to 990, and all these different transition period. So you can see for all these transition periods, they have the same width, but the center is different. And we'll apply these methods given the transition period is from 90 to 180. Okay, so that means the width is same. The correct width is correct to the true simulation data, but the center is wrong. In that case, you can see sometimes there's a power loss, sometimes there's a power gain, because the center is different. Sometimes the center is going earlier, and sometimes the center is going late. So there will be a power loss, either power loss or power gain in those simulation study. And also we listed the performance of other weighted log run tests.
The power gain seems due to the sample size larger.
I'm sorry, what?
The power gain in that case is due to the sample size larger than
actually, the sample size is calculated based on the transition period.
Okay.
Yeah. Basically, it still depends on the transition period. If it's earlier, then you may need less sample and fewer samples, and if it's later, then you need more. And then what if you try three other transition period, which is we have the correct center, but the width is different. In that case, also the sample size, we can use our numerical method to calculate the sample size. Sample size will not change that much. And in that case, the empirical power is close to 85% as expected. Because this change is not like the previous change, because basically the center is given. The only changing is width, so it's not that much change. So in that case, our method performs well better than others. Others is at most close is like 80 or 83%. Lastly, we check what if the wrong center and the wrong width. So still you can see there's sometimes power loss and sometimes power gain, depends on the true transition period. If the transition period is late, then we may get power gain. If the transition period is earlier, then we may get power loss. So the take-home message is like, if we don't know the true transition period, so we may choose our when we apply the weighted log test. How can we choose the transition period? We may prefer to choose the transition period is later than earlier, so that we may not get any we may suffer less power loss. Okay. And also we have the R program to implement our tests, and also we write it as a R package. We will add them to the current library. In the package, we have several main functions. One is to perform our proposed weighted log tests. And also we can use the function to do the sample calculation, the power evaluation. And there's another function to calculate the average, the hazard ratio, which I will not discuss. I may not have time to discuss it in this talk. So we applied our code to the data. So this data is this one, is the real data at the very beginning. For this data, there's obviously there's a delayed treatment effect there. You can see by region, it looks like it separated around close to like 3 to 4, and then there's a so what if we apply our method to this real data set? So the result is if we are using the weighted log test using the sigmoid weight, and suppose we are using the transition period from 0 to 4, and then applied the weighted log test, our weighted log test will give us the p-value is 0.0004. So that means for the hypothesis testing, that means the true hazard ratio is not equal to 1. So there is a delayed treatment effect, and the transition period looks like we choose 0 to 4, but we can in this case the alternative hypothesis is accepted. And so in our paper, we presented that actually our weighted log test is the score test for the weighted Cox regression. And we talked about how to obtain the estimate of the average hazard ratio, so-called AHR. And the details is in the paper. I don't have time to talk about this. And the next one is I want to talk about how to do the estimation. So using the same model, the hazard ratio model. Previously we talked about how to test the trial data. Then another question is like, if given some trial data, how to evaluate or how to estimate the transition period and also the hazard ratio lambda. In this model, there's actually three parameters. There's tau 1, tau 2, and a lambda. And how to estimate these three parameters. So the standard way is we write the likelihood function of this model. And so the question is, there's a H known T is the hazard ratio of the control arm. So how can we handle this term? Either parametric or non-parametric. Because so it totally depends how we treat the H known T. A more intuitive way is if we assuming the H known is a constant always. In that way, it simplifies our model. If H known is a constant, it will greatly simplify this model. And by that, we can actually write out its likelihood function explicitly. And then we can actually use the MLE to do the optimization to optimize this theta space. And then we actually can get MLE in this model. Suppose there's a tau 1, tau 2, there's a interval constraint on these two the transition period endpoints. And using this idea, MLE, we actually apply this method to the real data to this real data set. And the result is we have tau 1 is a 2.1, tau 2 is a 5.8. And this is we assume the H known is a constant, it's like that, and the lambda is given like that. So that means the transition period in MLE way, we estimate the transition period is from 2.2 to 5.8. But actually, we sketch the graph like this. So the dashed line is using the MLE to estimate these two groups, two arms. Okay. But when we do this estimation, one thing is that you can see for the blue one, the control arm one. Oh, sorry. Yeah. For the control arm one is oh, sorry. This is actually for this blue one. You can see the curve, the smooth curve is not that match perfectly with the real data set. Because the reason is because this constant H known is a very strong assumption. In real data set, we may not have that ideal assumption, like the control arm has a constant H known. Another challenge is that the likelihood function may not be easy to optimize. So in that way, estimated the hazard and the hazard ratio is a very hard problem. And so another idea is we can use KM survival curves and to estimate the tau 1, the tau 2, and the lambda. But it's also hard. So what if we talk about this simplified model? So there's not transition period, there's just a transition time, tau star. In this way, the hazard ratio is changing from 1 to lambda with a jump at tau star. In this way,
we ran out of time.
Yeah, I almost done, sorry, like 3 minutes. In this way, we can write out, if we have the Km plots of two arms, we can write out its survival function as S0t and S1t. And so we can take the S1t over S1t hat and take the integral to minimize the sum of squared difference between these two curves. And since the Km plots are step functions, so this integral is actually much easier to evaluate with the step functions. And we can actually get a minimized problem with tau star. We can get an interval estimator for tau star and a point estimator for lambda. So using this idea, we actually applied the method to the real data set, and then we get this result. The tau star is between like 2.9 to 3.3, and the lambda is about 0.48. And the curve is, looks like that. And this is much perfectly matched to the real data analysis, not like the MLE one. Okay. So lastly, basically the discussion for our method is we can design some adaptive design to early data to estimate the tau star or tau 1 to tau 2, the transition period. And further research also should needed to on this delayed treatment effect problem. And we have our programs and our packages, which is available upon request. And thank you for your time. Any questions?
Thank you very much. As we ran out of time already, the students can be free to go to their duties. And if you guys have questions, feel free to answer. I'm also